Spiking neural networks, or SNNs, are biologically inspired and highly energy-efficient models. They are ideal for edge devices. However, training SNNs is a challenge, especially for tasks like gesture recognition, due to their spiking nature. This project explores a method called distillation-boosted spiking neural networks for gesture recognition. SNNs use discrete spikes to transmit information, making traditional gradient-based training methods, like backpropagation, ineffective. On the other hand, artificial neural networks, or ANNs, achieve high accuracy, but consume much more energy and computing power. This project aims to bridge that performance gap by improving SNNs using a method called knowledge distillation, applied here for the first time on event-based dynamic gesture recognition. Knowledge distillation is a training technique where a large, well-trained model, called the teacher, guides a smaller or more efficient model, the student. Instead of learning from raw labels alone, the student learns from the soft class probabilities predicted by the teacher. This richer supervision helps the student model generalize better. In this project, the teacher is an ANN trained on RGB video, and the student is an SNN trained on event-based data. This project had 5 key objectives. 1. Train spiking neural networks using surrogate gradient methods. 2. Generate a gesture dataset in both RGB and event-based formats. 3. Apply knowledge distillation from a high-performing ANN to an SNN. 4. Compare the performance of direct SNN training versus KD-guided training. 5. Analyze trade-offs in accuracy, efficiency, and model size. We use the gesture dataset, which is a 27 different hand gestures dataset, originally in RGB format. Using a simulator called V2E, we convert these RGB videos into event-based data. Event-based data simulates how neuromorphic sensors work, by capturing only motion or changes in the scene. Our training pipeline consists of 2 paths. First, we train an SNN directly on event streams using surrogate gradient techniques. Second, we train the same SNN again, but this time with guidance from the ANN teacher model, using knowledge distillation. In the KD-guided path, the ANN, trained on RGB input, produces class probability distributions. These soft targets help the SNN learn better than just using hard labels. This guidance allows the SNN to model more precise decision boundaries. We tested different alpha values, which control the influence of the teacher's output during knowledge distillation. For the top 5 classes where the ANN performed best, using an alpha of 0.4 gave us a 5.49% accuracy boost compared to direct SNN training. For a random set of 5 classes where the ANN did not perform as well, the same alpha value of 0.4 still gave us a 2.6% accuracy improvement with KD over direct training. Our findings show that 1. SNNs trained with knowledge distillation achieve higher accuracy. 2. Training converges faster with KD. 3. SNNs had 55% fewer parameters than ANNs, only 4.9 million compared to 11 million, while maintaining comparable performance. In summary, knowledge distillation helps overcome the training challenges of SNNs and enables energy-efficient gesture recognition. To conclude, we demonstrated that knowledge distillation can bridge the performance gap between SNNs and ANNs. Our KD framework and dataset contribute to the field of energy-efficient deep learning for dynamic tasks. Future work includes real-time deployment on edge devices like neuromorphic chips, and extending the system to support multimodal inputs, such as gesture plus audio.